All right. So, last lesson probably makes sense, hopefully, in of itself. But what's going to end up happening with this lesson here? The rules for 6.2b are different than they were from A. So you've got these rules from last lesson that you already sort of understand, but what will happen if you're not careful is these two lessons will blend together in your mind and you'll get tripped up on when to use each set of rules. So the first thing I need to show you guys before we get into like the actual rules is how is this lesson different than the last one? Section 6.2a was called linear transformations of a random variable. So I have my x, my random variable, and I do numbers to that random variable. I can add, subtract, multiply, or divide a number to my random variable. Okay? And we learned those rules already. What's going to end up happening in this lesson is instead of just having one random variable, I'm going to take two separate random variables and I'm going to smash them together and combine them somehow to get a new random variable. So rather than doing numbers on a single random variable, we're going to take two random variables and combine them. And the rules for that scenario are different than the ones from last time. So we're going to kind of keep the same trend we were doing last time and talk about community college credit hours here. This top table here is just copy pasted out of last time's notes. So it's the credit hours from El Dorado Community College and the probability of the kids who have those number of hours. And I went ahead on the right side here and I put down a mean, standard deviation, variance for each of these two variables here. The second table is a new data set. This is a second community college where you can only take 12, 15, or 18 credit hours. Those are the only options available. You can't do 13 or 17. And what's going to end up happening in this problem is we are going to take those two separate tables and we're going to pair up a student from the first community college with a student from the second. We're going to establish a new random variable s. S is going to be the total number of credit hours between this kid and this kid from the other college put together. So I have x plus y right here, which means this is a combination of random variables, not a transformation, not a linear transformation here. So the rules are going to be new when you smash two different random variables together. Now I went ahead on this slide here and showed you guys the table of S. These are all the possibilities for S along with their probabilities. But I think it's worth reviewing right here where those numbers come from because this table here isn't magic. It's just using what's on the last page. If I were to randomly pick one kid from X and one kid from Y, the least number of credit hours I could pick from X is 12. The least amount from Y is also 12. So the total sum, the smallest it could possibly be, is a 24. So I would need a 12 and a 12 for that to happen. So if you do 0.25 times 0.3, that's going to equal 0.075. And the smallest number of credit hours is 24. Then let's go to 25. The only way you could get 25 in this scenario, it would have to be a 13 from over here and a 12 from over here. You couldn't go 12 with 13 because there is no 13 on Y. So if you do this 0.10 for the 13 times this 0.3, you're going to get 0.03, which is exactly that probability right there. That pattern will kind of keep going until you get to ones like 27 over here. You'll notice 27 has a much bigger probability than the ones around it. That is because with 27, there are multiple ways that you could make that happen. So it could be that you have a 12 over here with a 15 over here. So you're going to multiply those two probabilities. Or it could be that you have a 15 here with a 12 over here. So you'd have to multiply those two pairs and then add them together to get your actual total for the probability. So every table we did last lesson, every linear transformation, the probabilities on the bottom here stayed the same, which means if we graphed this and made a histogram, the histogram would have looked the same. The bars would be the same heights. The only thing is we would have erased our x-axis and put our new numbers for whatever variable it was. But when you combine two different random variables, first of all, we have more numbers up here than we used to, and the probabilities have also changed. So we talked earlier on in the school year about how nothing, add, subtract, multiply, divide, affects shape. Combining different random variables and smashing them together does change your shape. And you can't really tell what that shape is going to be until you actually just graph the problem here. So know that when you combine different random variables, the shape of your new distribution could change. So anyways, now that we've got a little bit of background here, let's go ahead and look at the new statistics here. I already typed in my data to the calculator. Sorry, I had a quick calculator issue to fix, but I went ahead and ran a one variable stats. Frequency list was in L2, and I got this data right here for my set. So again, typed in all the numbers, ran a one variable stats, etc., etc. So when you do that, you get this info here. And what I'm going to do is copy down the mean, standard deviation, and variance for this data set below. And I'm going to use all three of those quantities. So my mean for this problem, my new variable s, was a 29.65. I'm choosing to use the mean notation right there. I could have written expected value of s. That would be the same thing. And then moving on, I've got my standard deviation, which is 3.10. That goes on the third row, 3.10 for my standard deviation. And then they didn't give me a variance straight up that I saw. So all I'm going to do is just square my standard deviation so I can use that instead. And if I do a 3.0 blah, blah, blah squared, it ends up being 9.63. So the variance in this data set is a 9.63. Okay, so we've got our little stuff set up right here. And I want to make some observations with regards to our new data set for S. This is for S, which is just X and Y added together. Let's look at the expected value, also known as the mean, first. If you take your two old expected values and you add them together, you get your new expected value for S. The mean in general is great. We like the mean because it works exactly like common sense tells you it would in either scenario. No tricks, no craziness going on right there. Okay? The next thing I want to do, though, is look at the standard deviations. Because in the last lesson, we would know, oh yeah, don't worry about adding, but you're still going to multiply or divide the standard deviation. Now, clearly, the standard deviation changed because it's a 3.10 according to our calculator, but it's not just these two numbers added together. It's not. You could stare at this list of numbers here for the standard deviation and maybe eventually figure out how exactly they got from these to here, but it's not just a straight up addition problem, okay? But if you look at the variance, I didn't even bother talking about the variance in the last lesson because it didn't work out like we needed it to. The variances of my two random variables, if I add together this variance with this variance, I get my new variance over here for my new variable. So there's this thing, like before you take your square root on a standard deviation, we look at this variance, like why did we give this a name? Back in chapter 1, I said, oh yeah, we'll use it later. Don't worry about it. Just write it down for now. Learn the name. One of the things we use variance for in statistics, it is actually the variances that combine when you add or subtract two random variables. So we do not use the standard deviation directly. That's not going to work for us. What we do instead is we combine the variances to get our new variance for the problem. Okay? So that's not a mathematical like proof or anything that this works, but you can at least see through the example if you followed along in your calculator that it does work out for the context of this problem here. So let's go ahead then and talk about a few of these things. When adding or subtracting different random variables, you're going to treat the mean exactly like common sense says you should. So you're going to add or subtract the means. Just do what common sense says and you're in great shape. I didn't talk about the range in my example right there, and that's actually going to be easier to do with a quick sidebar example. So I am going to talk about the range really fast over here on the side. It's easier if I use two just like smaller data sets. So let's say my variable A was the numbers, 7, 9, and 10. And my data set B is going to be the numbers 2, 3, 4. So these are my two data sets. And I'm going to look at the new variable where I take a number in A minus a number in B. Actually, I'll start with plus. If I add a number over here from a number over here, let's look at the range of each of these possibilities. So if I do A plus B, the smallest thing I could get for my answer. Well, actually, let me find the original ranges first. The range of this guy is 3, and the range of this guy is 2. 10 minus 7, 4 minus 2. Let's look at what I can get out for C. The smallest thing that could happen for C would be 7 plus 2. So the smallest number I can get out over here is 9. I can get other things like a 10, 7 plus 3, but I'm not going to worry about those. I'm going to go to the biggest possibility, which is 10 plus 4, or 14. So the range for this new variable C is going to be 5, 14 minus 9. So that kind of makes sense. You add the ranges, you get your answer. Here's the part that probably you wouldn't have expected, though. Let's take that same exact problem. A is going to be the numbers 7, 9, and 10. B is going to be the numbers 2, 3, 4. But let's look now at A minus B. So again, the range for this guy was 3. The range for this guy was 2. If you take A minus B, I want the biggest thing first. The biggest thing I can get out from A minus B, I guess I can do smallest first. Doesn't really matter. Let's do smallest. Smallest number I can get out from A minus B would be the smallest over here minus the biggest over here. 7 minus 4 means the smallest answer I can get for this problem is a 3. And then if I take the biggest answer, that would be the biggest number over here minus the smallest number over here. 10 minus 2, the biggest thing I can get for A minus B is an 8. What's crazy about this one here, even though we were subtracting A and B, you can look at this problem and see the range is still a 5. In other words, range, and actually all measures of spread for that matter, gets added even if your variables get subtracted. So the mean, you add or subtract, just do what the problem says. But range, on the other hand, you always add. So even with subtraction. Okay. Now I like doing that with range because range is the easiest measure of spread to understand. The same logic applies to things like standard deviation, other measures of spread that we've learned about here. Even when you subtract random variables, you're taking two different things with variability and you're still combining them somehow, meaning your result will be even more variable than the old one. So even when you subtract, you have to add measures of spread. Okay? Now, the rules for variance and standard deviation. The first two things, mean and range, you don't need to know independence. But in order to actually do these calculations for variance and for standard deviation, you need to know that your different random variables are independent from one another. That's just a feature of standard deviation in general, is that it assumes independence between variables. So if you have a situation where the variables aren't independent, you can't do the standard deviation or variance calculations like I'm going to show you. So when you add or subtract independent random variables, if you know they're independent, the variances always get added. Add the variances. Standard deviation, on the other hand, you need to turn it to a variance first, and then add. And then square roots. So you basically convert it to variances first, combine those, and then take a square root to get you back down to where you need to be. Weirder process, harder to understand and harder to remember than last lesson, but really important that you can keep the two scenarios straight. So let's look at an example problem here. As we are jumping into this example problem, I got done earlier in the lesson saying that shape changes when you combine random variables. The exception to that, and it's a really useful exception, is with normal random variables. I'm not going to attempt to justify this to you guys in a proof or anything. I'm just going to tell it to you as a fact. Combining usually changes shape. So if you have two randomly shaped variables and you combine them, you don't know what's going to happen. Quick example of why that is, I already showed the probability example earlier. Let's say I have A, which looks like that, and I have B, which looks like this. And I combine this variable with this variable somehow. You don't know when they get combined if you're going to see like a full-on staircase like this, like a U-shape to your picture. You don't know if they're actually going to overlap more than that. Like this one goes all the way to over here, and you end up seeing like a staircase like this. That's a really bad picture. Or it could be somewhere else in between. Even if you know the shape of the originals, you can't really tell what's going to happen with your new shape until after you graph them. So like if these are my two variables, they could combine like this, or like this, or like this, or like this. We just don't know. Okay? So usually when you combine random variables, your shape is going to change. The exception to that, though, is with normal random variables. So, but normal variables stay normal when combined. When combined together, I should say. If you combine normal stuff, you still get a normal variable. Okay? So that is our basic setup for this problem here, or our basic idea going in. The shape is going to change unless they're normal, where it stays normal. So let's practice these rules, because there's a lot kind of flying around in this lesson that you have to be able to keep track of. This is a relatively challenging lesson that we're embarked on right here. We have x and y. They are independents. X is a normal random variable, and remember this notation right here means that this is the mean, and this is the standard deviation. And this is y's mean, and y's standard deviation. Both are normal. So first of all, what is the distribution of t and q? Both t and q are going to be normal, because we're combining normal random variables. Let's do t first. For the mean of t, what you're going to do is you're going to take the mean of x plus the mean of y. So I find that with this sort of problem, it's actually easier to make a little chart with everything that you have going on before you start. It's easier to diagram these problems out, and you'll see what I mean with this as I write them down. They didn't straight up tell me the variance, but I know that 3 squared is a 9. So those are the stats for x, and I'm also going to write the stats for y before I do my t. So y has a mean of 13. It has a standard deviation of 4, which means the variance for y, ooh, that was bad. I didn't write variance here. That's a squared. Variance for y is going to be a 16. All right, so now it's time to do t. For variable t, we're going to do the mean first. The mean is our friend. We love the mean. The mean does exactly what common sense says. All I'm going to do is add this mean with this mean. So I'm going to do 8 plus 13, and the mean of t is a 21. The standard deviation I cannot touch right away. The standard deviation I cannot just combine straight up. What I need to do is instead use the variances and combine those. So I'm going to find the variance for t next, and that's going to be 9 plus 16, which is 25. Okay? And then if I know the variance of t, all I need to do is take the square root of that variance, and I get the standard deviation for t. So t is going to be a normal variable with mean 21 and with standard deviation 5. There's a lot going on in this lesson that you have to be able to kind of process. Let's talk about q. And q is going to take the variable y minus the variable x. So the mean for q. Mean is common sense. You do what it says. Notice that y comes first here. So I'm going to take this mean minus this mean right here. So it's 13 minus 8, which is 5. Means can be negative. You can have a negative expected value. So if it was a negative number, that's totally cool. You just do what common sense says to do. The variance is going to be my next guy right here that I go for, because I can't get my standard deviation yet. And to get my variance here, even when you subtract, you add measures of spread. So you are going to add the 16 and the 9 together, even though it's subtraction, meaning you will get the same answer of 25 for your variance. And then finally, my standard deviation is still going to be 5. So Q is normal with mean 5, standard deviation 5. This takes a lot of practice to wrap your head around, but that is the basic setup right there. Now, if you're looking at these and you're starting to understand it and it's good, that's cool. But it does get more complicated because what we can do is we can blend the rules from last time and the rules from this time in the same problem. And that's what we're going to see in our next example here. We'll also do a practice activity with this in class, so no worries if this is confusing going through it. If you're feeling good, I recommend trying these yourself and seeing how it goes, but don't get discouraged if this is something that you are like, that's hard for you to do. All right, so we need to find the mean and the standard deviation for both C and D. C actually is just like the last slide, so this would be a good one to try for yourself. I would be super impressed with you if you got D right without my help here. So pause the video and at least try C, and then we'll see how it goes, and I'll talk you through it. So super recommend when you do these problems that you make the stats for each variable in a little table before you try doing the problem here. A has a mean of 11 and a variance, this time they give us a variance of 36. If the variance is 36, that means the standard deviation is 6. And then looking at B, B has a mean of 19. B has a standard deviation of 4, so careful where you're putting everything, which means the variance for B is 16. Okay, I really should have subscripts on all of these, but such is life, I guess. Putting down my little subscripts here. Now it's time for C. The mean for C, we got to take A minus B. So what I'm going to do for the mean of C is I'm going to take the mean of A minus the mean of B, which is going to get me a sweet -8 for my mean. Again, means can be negative, no big deal. Then I'm going to go for my variance because when I smash together different random variables, I use the variance, not the standard deviation. So what I'm going to do for the variance of C is take my 36 and my 16, which is going to get me 52. Then to get what they actually asked for here, which is the standard deviation of C, I take square root 52. So far our problems have worked out clean. This one won't. Frequently it won't. It's about 7.21 for my new standard deviation. In the problem, I failed to mention this, but it did say the variables were independent. If it didn't say that, you couldn't do your standard deviation or your variance. All right, so hopefully some of you guys were able to get that when you actually tried it out for yourself. And that would be a good thing. It means you're really understanding what's going on. D is genuinely challenging. The reason that D is so challenging is because it not only smashes together B and A, but it does numbers on B and A as well. When you do constants to a random variable, you do them in the last lesson, like we learned, to the standard deviation, not to the variance. You cannot just multiply the variance by 2 or by 4. So what's going to happen here is I'm going to write down, I think the best way to do this problem is to do each of these pieces separately first. So D is going to be 2 times B. So I'm going to find my stats for that piece, that 2 times B piece. And the mean of B is 19. So the mean of 2 times B, it's going to be a 38. So I just did 2 times 19 for my new mean for just that bubble right there. The variance for B, for this piece for 2B, I cannot actually get right now. You do not just multiply a number to the variance. You actually do the number to the standard deviation. So I'm going to get this piece of my answer first. B had a standard deviation of 4. That means the standard deviation of this bubble is going to be 8. That's 2 times 4. And if I know that, then I can fill out my standard deviation, or my variance, which is going to be a 64. It's kind of weird. It's like a little puzzle you have to figure out in the right order here. Okay, that's my first bubble. Then I'm going to take my second bubble. The mean for the 4A part, I'm ignoring the minus for right now. I have to take 4 times the old mean of A, which is going to be 44. Can't get my variance right now. Going to save that guy for a sec because constants they're not applied to the variance. You're going to apply constants to the standard deviation. So the standard deviation for A doesn't tell us, actually. It tells us the 36. That means it's 6. Found that over here. So that means 4 times 6 is going to be a 24 for the standard deviation of 4A. Then I got to square that, which is 576 for my variance. So I got myself my 2 blue pieces here and here. Now I'm ready to actually combine those 2 pieces, which means doing my subtraction. So I'm going to take for my final answer for D, the mean, this piece minus this piece. 38 minus 44 is a negative 6. Okay. Variance comes next. Even though I am subtracting, I'm going to go ahead and add my 2 variances together. So I have to do 64 and 576, which is a 640, it looks like. And then I have to take the square root of 640 to get my final answer, which is 25.30 if I round it. So you'll get used to kind of working your way through these problems here, but this last one especially is genuinely kind of difficult. But we'll do a bunch of practice of that in class when I see you guys. So we have one more big problem to talk about in this video right here. So take a deep breath, pause me if you need to. I'm kind of throwing a lot of content your way right here. But we're going to talk now about a bag of apples. All right, and the bag of apples has 12 different apples in it. Each apple follows a normal distribution, approximate normal distribution. The mean of an apple is 9, and the standard deviation of is 1.5. So we're going to say, I'll define a variable here. Let's say A is the weight of an apple. The mean of A is 9, and the standard deviation for A is a 1.5. And then what we're going to do is we're going to look at a bag that has 12 apples in it. Okay? If I asked you to give me a formula for the total weight, what I am guessing almost every single person I've ever talked to about this, virtually everybody, says is, well, if I want to have a variable for the bag, why wouldn't it just be 12 times A? That seems logical. An apple is right here. So a bag is 12 apples. Why can't I do this? This is actually incorrect, what they have written down. And the reason it's incorrect is because if you do it this way, you're acting like your 12 apples are exactly identical to one another. Because you're taking one apple and you're multiplying that one apple by 12. So that's not actually how you're allowed to do a problem like this, because that forces the apples to be identical. When you guys know, when you eat a bag of apples, some are going to be smaller than others, some are bigger. So what you actually have to do, this is not the right way, unfortunately. You're going to set up a variable B, and what you have to do is look at this variable as 12 different apples added together. So I'm going to set this up as A1 plus A2 plus A3 all the way up to A12. And this will get me my bag of apples altogether. Okay? So it's a little bit weird why you have to do it that way. But basically, if you do the 12 thing, that makes the apples identical, which isn't the case. You need 12 separate apples right here. So they asked us to do a probability. So we have a few steps to go yet. The mean of B. All I'm going to do is add the mean of A. Well, an apple has a mean of 9. The mean of A2. That also has a mean of 9. That also has a mean of 9. All the way up to the 12th apple right here. So what basically happens, it actually is the same for the mean as it would have been right here. You just do 12 times 9. And the mean for B is going to be 108. Now, the standard deviation for B. You cannot find the standard deviation straight up because A1 through A12 are all different random variables. So what you have to do is actually take the standard deviation of an apple and turn it into a variance. So this guy's variance right here would be a 1.5 squared, whatever that is. And then I would do another 1.15, and I'm going to leave it like this instead of multiplying it out, just because I think it's easier to see what's going on. So you're going to do that 12 different times. You're going to add all those variances together, and at the end of the day, you'll take a square root to turn it back into a standard deviation. Finding standard deviation without finding the variance first is kind of like doing Pythagorean theorem in a way, but basically you just do the variances, add them up, and then take a square roots. So if I do that, what's really going to happen is I'm going to have 1.15 squared, which is 2.25, and I'm going to have that 12 different times. So I can write that as 1.5 squared times 12, or I can do just like this. And if you type that in and actually calculate the answer here, the standard deviation is like 5.20 if you round this. So I've just done a bunch of work that shows that B follows a normal distribution, approximately normal, with a mean of 108 and a standard deviation of 5.20 using the rules from this chapter. Now, they made us do even more than what I just did right there. They ask us to find a probability. So they ask us, what is the probability that all 12 apples, so that's the bag that I got going on right here, all 12 apples is less than 100 ounces. So what I would do is I would draw myself a normal curve. My mean for B, so B is the bag weights. The mean is 108. The standard deviation for B is that 5.20, and they're asking about the probability of 100 or less than 100, but remember it doesn't matter if you less than or equal to, for a continuous random variable. And if you do your normal CDF on this one, I'm not going to write out the work for it, I'm just going to tell us the answer here. You get about 0.062 for your probability. So if this was a free response question, you would show the normal CDF, you would restate in words, but once you actually get your new stats for B, you run a normal CDF, and then you can get your probability that way. So these problems here are fairly complicated and will definitely take some practice for you guys to get used to. Okay, the last thing I need to talk about in this lesson, and I know it's been a lot already, I just want to do a real quick thing. We're not going to do calculations here. In general, going to a casino betting is just you need to go in expecting that you will lose money. I never gamble because I know that the odds are against me. It's just like I don't enjoy losing money. But if you were going to gamble, you should have a set amount, like when you get older, of course, and you're like legal to gamble, you should have a set amount of money that you're going to bet and not go over that if you insist on going at all. But let's talk about what is the better bet, mathematically speaking here. If you have $100 that you're going to spend, is it better to place it all at once on one bet, or to make that same bet with $1 100 different times? The expected value will not change. The mean is the same and it's negative for both scenarios here. So you're going to lose money in the long run no matter what. So the idea is if you're going to lose money in the long run no matter what, playing lots of times is just going to make the odds work out like they're supposed to, and you're going to lose money. So if you insist on gambling on something, it's better when the odds are not in your favor, i.e. every casino game ever, to basically make the bet with a higher standard deviation. This bet of $100 at once is going to have a higher standard deviation. So maybe you defy the odds and you happen to win in that one bet because the long run probability hasn't kicked in yet. Or maybe you lose all your money. You probably still lose all your money, but you have a better chance of coming out with a profit if you do this first bet right here compared to the second one, because in the long run, things don't work out in your favor, and the top bet has a higher standard deviation and variance. So a tough section, guys, with a lot in it. We'll practice it when you get to me in class, but that is all I have in 6.2.